Hi, this is lecture number 3 on linear transformation. In this lecture, we are going to discuss about isomorphism and isomorphic vector spaces. So the topics covered in this video lectures are 1-1 transformation, that is also called injective transformation, onto transformation, or we call this subjective transformation, 1-1 and onto transformation, isomorphism, singular and non-singular transformations, and then after that we will discuss some examples related to these. So let us start our discussion with what is 1-1 transformation. So this is definition number 1-1 transformation. That is also called injective transformation. So let T is a mapping from, let V and W be two vector spaces. V and W be two vector spaces over the same field. Field that is F, right? And T is a mapping from V to W. This be a linear transformation. Then T is said to be 1-1 or injective. If and only if for all x comma given any x comma y belongs to V, such that T of x equal to T of y implies x equal to y. So if given any x and y, x, y belongs to vector space V, with Px equal to Ty, this implies x equal to y. Or the contrapositive of this statement is, given any x comma y belongs to V, x comma y belongs to V, with x is not equal to y, such that, or this implies such that T of x, or we can write this as, this implies T of x is not equal to T of y. So this first one and second, both are same, but second is the contrapositive of first one. What is contrapositive? If we have a statement, S is my statement, if P, then Q. If this is my statement, what is the contrapositive of this statement? Contrapositive of S. Contrapositive of S is if not Q, then not P. So here this is our P, and this is Q. So if P, then Q. What is the contrapositive? If not Q, not Q means X is not equal to Y. If not Q, this is not Q, then not P. Tx is not equal to Ty. So both are, if statement is true, if statement is true, then its contrapositive is also true. So both are equal. So in this way we can say this is true, right? So we can use any one of them, but most of the time what we observe, when we prove that T is 1 1, we use first one. So now second is definition number 2, on to transformation, or we call this transformation as surjective transformation. So let V and W be two vector spaces over the same field capital F, and P is a mapping from V to W be a linear transformation, then T is said to be onto or surjective if and only for given any, for all Y in W, there exists X in V such that T of X is equal to 1. So if we have a vector space V and vector space W over the same field F, and T is a mapping from V to W. So given any, if we pick any Y in W, so there exists some X, at least one. Right? There exists one X for this Y such that T of X equal to Y, such that T of X is equal to Y. Right? Even we have more than one. There may be more than one, right? So, but at least we have one X. So, if there exists an element X such that T of X equal to Y, then the transformation is said to be onto transformation. In this case, what we observe that given any, it is true for each and every element of domain. If every element of domain has pre-image, then it is said to be onto. So what we observe that in this case, if T is onto, transformation is onto, then that is, we can also say that range of T is equal to W. If range of T is equal to W, every map has its image. Each and every element of Y is associated to an element of domain. So if range of T is equal to W, then T is said to be an onto transformation. Or this means that T of V, transformation output of the whole domain, that is T of V, V is a vector space and its output T of V that is equal to W. Then we call this that W is the T is onto transformation, right? Where range of T, we denote this by RT. And how we can define range of T? Range of T is equal to set of all of T of V such that V belongs to vector space V. So it is true for that every element of domain has image T of V. Then the range of T is the set TV for all V in domain V in V, capital V, vector space V. So what we conclude from these, if the mapping E from V to W is on to, then range of T is equal to T of V whole vector space, that is equal to W. So this is again another definition of onto transformation, that a mapping T from V to W is said to be onto if range of T is equal to whole codomain. Range of T is equal to codomain. So in this way we can define onto transformation, or we call this surjective transformation. Now next is one onto transformation, or we call this bijective transformation, one and onto. So again, V and W are defined over the same two vector spaces over the same field F. So we can say T from V to W be a linear transformation, and T is said to be bijective, one onto, or bijective if and only if for every Y belongs to W there exists unique X belongs to V such that T of X is equal to 1. Or we can say if T is both 1 and onto, then it is called bijective. But in terms of quantifier, how we can define? So this is very important. So in terms of quantifier, quantifiers, we can write given any Y in W, there exists unique. This is a symbol for uniqueness. There exists unique X in V such that T of X is equal to Y. So this is how we can say the transformation is bijective transformation. So if we have a vector space V over the same field and W over the same field F, T is a mapping from V to W. So given any, if we pick any Y in W, so there exists unique. It means we have only one T image of this Y such that T of X is equal to Y. T of X is equal to. So in first we have an element associated to this Y. For given any Y in W, there exists X in V, right? So there exists X in V such that, and this x is unique. There exists unique x in V, such that T of x is equal to. So in previous, in on to, we have given any y in Y, there exists x in. So here we are not talking about uniqueness. There may be another y x. Let this be x1, this be x2, right? Such that T of x2 equal to y. There may be another element x3, so that T of x3 equal to y. So y may have more than one premiss, but for bijective, you give me any element from W, but this element has unique x in V, because it is 1 1 also. If it has more than one, if there is another x, then let this be x1 and this be x2, then T of x2 equal to y, but it is not 1 1. In this case, T of x2 equal to y and T of x1 equal to y. X1 and x2 are different, but their image are same, then it is not 1 1. If it is not 1 1, then it is not bijective. So in this case, T is bijective if and only if for all y in W, there exists unique x in V such that T of x equal to y. Then only we can say that T's transformation is bijective. Or we can say if T is bijective if and only if T is bijective if and only if T is 1 1 and 1 2. Right? So then the transformation is said to be bijective transformation. Now next definition is isomorphism So let V and W be two vector spaces over the same field F, and T is a mapping from V to W, and it is a linear transformation, V a linear transformation. Then T is said to be an isomorphism if and only if T is 1 1 and onto, that is bijective. So if the transformation is, if T is a linear transformation, then T is said to be an isomorphism if and only if T is 1 1 and onto. That is, if T is bijective, then T is isomorphic. That is, T is an isomorphism if and only if T is bijective, right? So how we can say T is bijective? If and only if for all y in W, or we can say given any y in W, there exists unique x in V such that T of x is equal to y. So if T is isomorphism, if and only if it is bijective, if T is bijective, then T is an isomorphism. Okay. Definition number 5, non-singular transformation. We know that every linear transformation can be written as can be written as a linear combination of so every linear transformation can be written in term of matrix, and every matrix can be written in term of linear transformation. Every linear transformation can be represented in term of matrix, and every matrix can be written matrix can be written in term of, or can be expressed in term of linear transformation. So this is very important. If every transformation can be written in term of matrix, so it means it satisfies the properties of matrices. So if we have a matrix A, we have a matrix A, 1, 2, 3, 4. Then a matrix is said to be singular matrix if its determinant is 0. Then A is singular. A is singular matrix. And if determinant of A is not equal to 0, then A is non-singular. Right? A is non-singular matrix. So we know that determinant of 0 matrix, that is equal to 0. So this is singular matrix. But determinant, we have non-zero matrix, that is 1, 0, 0, 0. Again, the determinant is 0. This is again a singular matrix. Now, we have one matrix that A is equal to 2, 3, 3, 2, 3, 3, 9 by 2. The determinant of this matrix, that is equal to 0. So this matrix is said to be singular matrix. But if we take this matrix, then determinant of A, that is equal to 2 minus 9, that is minus 7, which is not equal to 0. Then A is non-singular matrix. A is non-singular matrices. Matrix. Right? So we use the concept of this in transformation also. So next definition is definition number 5. Non-singular matrix or non-singular transformation, not matrix, non-singular transformation. Let V and W be two vector spaces over the same field F, and T from V to W be a linear transformation, then T is said to be non-singular transformation if and only if given any x belongs to V with x is not equal to 0, x is not equal to 0, this implies T of x is equal to, T of x is not equal to 0. if we have a non-zero matrix, you give me any x from vector space V, but x is not equal to 0, then, and this implies that if T of x is also non-zero, then the transformation is said to be non-singular transformation. So if x is not equal to 0, because T be a linear transformation, and in linear transformation, T be a linear transformation. So we know that T of 0 is equal to 0, right? So if T of 0 equal to 0, and 0 is the 0 vector of this 0 is this 0 means we can also write or P of 0v. This 0v is the 0 vector of V, and T of 0v equal to 0w. This 0w is the 0 vector of W. So we know that if here, what is the null space of T, nullity of T? In this case, if we have only one, T of 0v is equal to 0w, only 0v maps to 0w, then null space of T, that is equal to only single element, that is 0v. Or we can say that is equal to nullity, right? So null space of T equal to 0 vector. So this implies we can say that is null space of T that is equal to singleton 0v, and that is also equal to nullity of, or we can also say if x is not equal to 0v, T of x is not equal to 0w, right? T of x is not equal to 0w. So this is equal to n. Or the same way, if we have a statement, this, if this is my statement, what is the negation of this statement? Or we can say what is the contrapositive of this statement? Not negation, but the contrapositive. We have already discussed. P implies Q. If P, then Q. Here P is x is not equal to 0v, and Q is Tx is not equal to 0w. So what is the contrapositive? For given any x in V with P of x is equal to 0w. If T of x is equal to 0w, this implies that x is not equal to 0v. What is the negation of this? That is x is equal to 0. If T of x equal to 0w implies x equal to 0v, where 0v and 0w are 0 vector of v and w respectively, then T is said to be a non-singular transformation. So quickly, what we write, what we find there, that given any x in V with x is not equal to 0v, this implies T of x is not equal to 0w. Or the contrapositive of this, if this is true, then its contrapositive is also true. So what is the contrapositive? Given any x in V, Tx is equal to, if Tx is equal to 0w, this implies, because negation of this is, if P is this, not Q is this. So not Q, Tx equal to 0w implies not P, that is x is equal to 0. So this is also true. So we can use both the definition. Okay? In the same way that we have discussed in 1.1. So we have we can use this one, or we can also use this one for non-singular transformation. So next definition is singular transformation. Singular transformation. So again, let V and W be two vector spaces. Vector spaces over the same field F, and T from V to W be a linear transformation. Then T is said to be singular to be singular if and only if there exists x is not equal to 0, or we can say there exists x belongs to V with x is not equal to 0V. Right? So we have non-zero vector x is not equal to 0V, right? Such that, but its output P of x, this is equal to 0W. We have non-zero element in V, but whose image is zero vector in W, then such type of transformation is said to be a singular transformation. Right? So how we can write this? So T is said to be, T is singular if and only if there exists x is not equal to 0V belongs to V, such that T of x is equal to 0W. So T is said to be singular. If T is singular, then it satisfies this. If x is not equal to 0V, if we have a non-zero vector in V whose image is Tx equal to 0W, then T is said to be singular. Right? So let us discuss some examples. Example 1. Show that the linear transformation T from R2 to R defined by T of x comma y is equal to x is onto but not 1. So T is a mapping from, so we have an element T from, this is our domain R2 and this is codomain R. T is a mapping from R2 to R. So it is onto means if we pick any element for all y, for all element in from R, there exists an element in R2 such that T of x comma y, if we take xy in R2, T of x comma y is equal to x, right? So if we pick any element, if we take any element, then its pre-image, there exists x comma y such that T of x comma y is equal to this. It means every element of codomain has pre-image in domain. So now how we can prove this? But what we observe in this question, P of x comma y, the image of x comma y is x, the first coordinate. Right? So if we have x comma y here, if we have a line, this x is fixed, and this. So here what we have, x comma y1, because here x is same, y here y1, here y2. What is this point? X comma y2. What is the point? If we take y3 here, this is the point x comma y3, and all, right? So what we observe here, that the output of P of x comma y1 is also equal to x. So this is P of x1 comma y1, x comma y1. What is the output of Px comma y2? It is again x, because we get the first coordinate, first entry. P of x comma y3, it is again x. So what is the image of all the element on this line? Each and every element on this line maps with x. So this element x has pre-image all the elements on this line. So every element on this line is the pre-image of this x. So what about this? If we choose this x, we choose this, let it be A. So every element on this line, this maps to an element A. So is it 1 1? No, this is not 1 1, because x comma y1 output is also equal to x comma y2 is also equal to x, but both points are not same, but their output is same. Then this is not 1 1 transformation, but this is onto, because given any element in codomain, that element, there exists an element in domain such that T of that element is equal to x, right? So we have, if we pick any x, if we pick any x, so let this be this point, right? So I denote this by another color. If this is our x, so what is the pre-image of this x? The pre-image of this x is the whole line. So we have at least one element, but there are infinitely many elements whose image is x, right? So this is onto, but this is not one. But how we can go for the proof? So the given linear transformation is E of x comma y is equal to x. P is a mapping from R2 to R. So E of x y equal to x. This is defined. So first E is onto. We prove that E is onto. How we can write? For any given any y, or we can say given any x in R, given any x in R, there exists the definition. If we take let it be by, or let it be given any x in R, there exists x comma y belongs to R2 such that E of xy is equal to x. So P of xy equal to x. This is how we define the linear transformation, right? So you give me any x in real number R. There exists, we have at least one element in R2 such that E of xy, the image of that element is equal to x. How we can prove this, right? So let us take, let x be any element R. X belongs to R. This implies that x comma 0, if we take any element x comma 0, then this belongs to R2. Yes, this belongs to R2. This is the element x. This is the element x comma 0. X comma 0. The image of this element is x, right? So you give me any element x in R, this implies x comma 0 belongs to R such that t of x comma 0. What is the image of tx 0? That is equal to x. So this implies that t is onto. Even we can take any, we can also prove this, that given any x in R, there exists x comma y in R2 such that t of x comma y, that is equal to x. Here in this, what we do, we fix y equal to 0, right? So you can take y equal to 1 also, you can take y equal to 2 also, x comma 2 belongs to R2, so that t of x comma 2 equal to, that is t of, we can also write this as x comma 1 belongs to R2, such that t of x comma 1, that is also equal to x. So we have to find at least one element. So there are so many elements. Even there is a complete line whose image is the point x, right? So this is the general case. Here we take x y equal to 0, but we can also go with this part, or we can do, right? So I can write, or you can do this in this way. So this is the general part. You can take any y. So t is on. So first part is done. Now what is the second part? What we have to do? T is not 1 1. Not 1 1. So but how we can go for t is not 1 1? What is the definition of t to be 1 1? That given any x comma y belongs to V, tx equal to ty implies x equal to y. Or we can say, or the second definition, if we take distinct element in domain, then we have distinct image in codomain. So if we have x comma y, y1, this belongs to R2, and x comma y2, this belongs to R2, right? Y1 is not equal to y2. With y1 is not equal to y2. So points are different. X y1 is not equal to x y2. So here we can say x comma y1 is not equal to x comma y2. So we have distinct point. So we have to find that their image is also distinct if it is 1 1. But if it is not 1 1, then its image is same. So what is the image of tx comma y1? It is x. And what is the image of tx comma y2? That is again x. So this implies that t of x comma y1, that is equal to t of x comma y2. So x comma y1 and x comma y2, we have two elements in R2 with x comma y1. X comma y1 is not equal to x comma y2. This implies t of x comma y1 is equal to t of x comma y2. In this way, we can say t is not 1. Pause, revise, and then proceed. Next example. T from R3 to R2 be a linear transformation defined by P of x comma y comma z is equal to x comma y. So we have to show that P is onto but not 1. So again, if we look at the transformation, this is our plane R3 and this is R2. If we pick any point x comma y comma z1, what is the image of this point? The image of this point is x comma y. But if we take any other point x comma y comma z2, right? So what is the image of this point? Again, we get the same point. Is it a 1, 1? No, we have two distinct points, but whose image is same. So it is not a 1, 1 transformation. But it is onto. You give me any x, y in R2. This is R2. There exists a point in R3 such that whose image is x comma y. Is the point clear? If we think like this in terms of quantifier, then the definition become very, very simple. So how we can solve this? So the given transformation P x comma y comma z is equal to x comma y. So first t is onto. So onto what we do? Given any, you can take any x comma y in R2 such that there exists x comma y comma z in R3 such that even we can take a comma b comma c in R3 such that t of x comma y comma a comma b comma c equal to x comma y, right? But because the transformation is given in terms of x comma y, so we can take for given any x comma y in R2, there exists x comma y comma z in R3 such that t of x comma y comma z is equal to x comma y. So if we take x comma any element, right? If we take, even it is true for any z belongs to, all z belongs to R, but it means x comma y, this belongs to R2, then we have to find at least one element. What is that element? This implies there exists x comma y comma 0. This belongs to R3 such that p of x comma y comma 0 that is equal to x comma y. Can you tell me one more point whose image is x comma y? Yes, there exists x comma y comma 1 in R3 such that p of x comma y comma 1 is also equal to xy. Yes, it is. You give me any point in R2, there exists at least one point in R3 whose image is x comma y. So t is on 2, right? So we can write that t is on 2. This implies that t is on 2. Now t is 1, 1. T is 1, 1. So not 1. T is not 1. So given any x comma y, even we can take x1, y1, z1, and even instead of taking x1, y1, z1, we can take x comma y comma z1 and x comma y comma z2 in R3 with z1 is not equal to z3. That is x comma y comma z1 is not equal to x comma y comma z2. This implies T of x comma y comma z1. What is the image of this? That is x comma y. And is it equal to T of x comma y comma z2? Yes. The image of T of x comma y comma z2 is also equal to x comma y. So points are different. Points in domain are different, but their image are same. And it is not one. This implies T is not 1. So in this way, we can prove that T is onto, but T is not 1. Example number 3. T is a mapping from R2 to R3 defined by T of x comma y is equal to x comma x minus y comma x plus y is 1 1 but not onto. This is 1 1 but not onto. So given transformation, given linear transformation is T of x comma y is equal to x comma x minus y plus y. So first T is 1 1. How we can go for this? We can take any x1 for all x comma y belongs to R2, or we can take given any x1 y1 x2 y2, this belongs to R2, then T of x1 y1 is equal to T of x2 y2. It is given. So if now we use a contrapositive condition of 1. So T of x1 image are equal. Now what we have to prove? That points are same, right? So it is given tx1 y1 equal to tx2 y2. What is the transformation? That is x comma x minus y comma x plus y. So output of this is x1 comma x1 minus y1 comma x1 plus y1. And this is equal to x2 comma x2 minus y2 comma x2 plus y2. Now two order pairs are equal. How they are equals? If each element of each and every element of the order pair are equal to the order pair of second element. That is, if x1 is equal to two order pairs are equal, if x1 is equal to x2, x1 minus y1 equal to x2 minus y2, and x1 plus y1 equal to x2 plus y1. Since from first we get x1 equal to x2, if we put this in second, so we get x1 equal to x2, y1 equal to y2. So both are equal, right? So this implies that x1, y1 is same as x2, y2. So we start with tx1, y1 equal to tx, y2, and we get x1, y1 equal to x2, y2. This implies that t is 1, 1. So first part is done. Now t is on 2. T is not on 2. It means you give me any element in R3, there does not exist any element in R2 such that whose image is not equal to R3. So for particular, if I take 0, 0, 1, this belongs to R3. So we have to find an element whose there exists an element in R2 whose image is 0, 0, 1. Is there any element whose image is 0, 0, 1? So let us check. So if this there exists, if we take this element in R3, there exists x comma y in R2 such that p of x comma y that is equal to 0, 0, 1. But what is t of x y? It is x comma x minus y comma x plus y. That is equal to 0, 0, 1. So we get x equal to 0, x minus y equal to 0, x plus y equal to 1. So here x equal to 0, so y equal to 0, x equal to 0, y equal to 0. Is it satisfy third equation? Is 0 plus 0 equal to 1? Not possible, right? Not possible. Which is not true. Therefore, there does not exist x comma y in R2 such that t of x comma y is equal to 0, 0, 1. It means every element of R3 has no t image. We have one element whose t image does not exist. It means that t is not on to. So t is not on to. Even you can take any other element. We pick one element in R3, 0, 0, 1. You can take another element 0, 0, 2, 0, 0, 3, 0, 0, 4, and so on. So there are so many elements whose t image does not exist. It means if we have a one element in codomain whose t image does not exist, then it is not on. It is not on. So exercise to all of you, try. T is a linear transformation from R3 to R2 defined by P of x, y, z equal to x minus y comma y. So t is what we have to do. T is on 2, but not 1, 1. This is first, and second, T is a mapping from R3 to R3 defined by P of x comma y comma z is equal to x minus y, even P of R3 to R2. This is P of R3 to R2, x minus y comma y. Again, you have to show that T is on 2, but not 1, 1. So try these examples. We will discuss theorems related to this topic in the next lecture. Thank you. Have a nice day.